the side of Mars we almost never see. Japan discovered something on the far side of Mars. But there is a problem with that sentence. The discovery has not happened. Not yet. And that may be more unsettling than any discovery you could invent. Because unlike the moon, Mars does not have a permanently dark far side. Mars rotates once every roughly 24 hours and 37 minutes, so every part of its surface eventually turns toward the sun and away from Earth. When scientists say the far side of Mars, they usually mean the hemisphere that is facing away from us at a particular moment. And Japan has never sent a successful spacecraft into orbit around Mars to investigate that hidden hemisphere. Japan's first Mars probe was Nozomi, launched in 1998. Its mission was designed to study the Martian upper atmosphere, the solar wind, the magnetic environment, and interactions between Mars and the space surrounding it. But after a series of technical problems and major trajectory changes, Nozomi never entered orbit around Mars. In December 2003, the mission was abandoned. The spacecraft continued onward as an artificial planet orbiting the sun near Mars. Site Turn Search 4 Turn Search 7. So if Yo Penny's photograph of something impossible on the hidden side of Mars, stop for a moment. Because the real story is stranger. Japan is preparing to return to the Martian system. And this time, it is not going after Mars itself. It is going after one of the planet's moons, Phobos, a small, irregular world that races around Mars so quickly that from its surface, Mars would dominate the sky like a gigantic red wall, a world that may be an ancient fragment of Mars itself, or an asteroid captured by Martian gravity, or something in between. Japan's Martian Moons Exploration Mission, MMX, is designed to investigate exactly that mystery. And according to JAXA, it is scheduled for launch in fiscal year 2026. The spacecraft is expected to reach the Martian system roughly 1 year later, study Phobos and Deimos, land on Phobos, collect more than 10 grams of material, and eventually bring those samples back to Earth. Site Turn Zero Search 19. That me has not happened yet. It is waiting in the dark. And when you understand what scientists think may be hiding in that darkness, the phrase far side of Mars begins to mean something much bigger. Because Mars is not simply a red planet, it is a graveyard of worlds. 4 billion years ago, it was not the frozen desert you see today. Mars had a thicker atmosphere. It possessed flowing water. Rivers carved valleys across its surface. Lakes occupied ancient basins. Volcanic eruptions reshaped entire regions. And then something changed. The atmosphere thinned. The surface became colder. Liquid water largely disappeared from the open landscape. And Mars entered the long, brutal transformation that created the world we see today. But the evidence of that ancient Mars is not evenly distributed. Some regions are ancient, some are relatively young. Some have been blasted by enormous impacts. Some have been buried beneath volcanic material. And some may preserve geological information that has survived for billions of years. That is why looking at Mars from the opposite side matters. Imagine standing in a giant library after a fire. Most of the books are damaged, some are completely destroyed, but hidden in a basement behind a wall nobody noticed are shelves that survived almost untouched. You would not begin by reading the books that are easiest to reach. You would search for the ones that survived. Mars works the same way. Its surface is a record of its history. Every crater is a timestamp. Every valley is a scar. Every mineral is a chemical clue. Every buried layer may preserve a chapter from a planet that no longer exists. and the far side can contain geological environments that are difficult to observe from Earth at any particular moment. But there is another reason Japan's story matters, because Japan has already demonstrated something extraordinary. The country became one of the world's most capable spacecraft sample return nations through missions such as Hayabusa and Hayabusa 2. Hayabusa 2 traveled to the asteroid Ryugu, operated around it, descended to its surface, collected material, and returned that material to Earth. Now Japan is attempting to apply that philosophy to the Martian system, not simply photographing a distant object, not merely flying past it, touching it, sampling it, bringing pieces of it home. That distinction changes everything. A photograph tells you what a surface looks like. A spectrometer tells you what chemicals may be present. But a physical sample gives scientists something far more powerful. They can crush it, heat it, dissolve it, examine its minerals under microscopes, measure isotopes, search for organic compounds, compare different grains, and perhaps most importantly, they can repeat those measurements years after the spacecraft has disappeared. That is the difference between visiting another world and bringing that world into the laboratory. And MMX is being built around that idea. The spacecraft is not simply a camera with an engine. It is an entire scientific laboratory compressed into a machine that must survive deep space. JAXA describes MMX as a world-first mission to return samples from the Martian region. Its scientific objectives include determining how Phobos and Deimos formed, reconstructing the evolution of the Martian system, and investigating how water and organic materials may have moved through the early solar system. Cite Turn Search 5, their S for the moons. One possibility is catastrophic. A massive impact may have struck young Mars, throwing enormous quantities of material in orbit. That debris could have eventually gathered together and created the moons. The other possibility is more deceptive. Phobos and Deimos may be captured asteroids. If that is true, then they did not originate with Mars at all. They came from elsewhere. They are strangers trapped in the gravitational prison of the red planet. And if scientists can determine which story is correct, they will learn something far larger than where two moons came from. They will learn how Mars itself was assembled, how material moved through the young solar system, and perhaps how the ingredients required for water, chemistry, and habitability were delivered to rocky planets. That is why the real Japanese mystery is not a secret structure on Mars. It is the history written into the rocks surrounding Mars. And somewhere inside that history may be an answer to a question that has haunted planetary science for decades. Was Mars always destined to become a frozen desert? Or did something happen to transform a once wet world into the hostile planet you see today? Japan is preparing to look for the answer. And when MMX finally enters the Martian system, it will not be looking at Mars as a simple red sphere hanging in the blackness. It will be looking at Mars as a crime scene, and Phobos may be the evidence that survived. The Mars you think you know is only half the story. You have probably seen Mars thousands of times. A red sphere, a few dark patches, white polar caps, maybe a photograph from a rover with a rocky desert stretching toward the horizon, and your brain quietly fills in the rest. You imagine that this is Mars, but it isn't. It is a tiny fraction of Mars. Even after decades of spacecraft exploration, enormous portions of the planet remain poorly understood. The reason is brutally simple. Mars is enormous, and spacecraft are painfully slow. The planet has a surface area of roughly 145 million square kilometers. That is smaller than Earth, but still vast enough to make exploration from orbit feel like searching an entire continent for individual fingerprints. Now imagine trying to understand that world while sitting millions of kilometers away. You cannot simply point a telescope at Mars and see everything. Earth's atmosphere interferes with observations. Dust storms can hide enormous regions. Seasonal changes alter the appearance of the surface, and the planet itself is constantly rotating. One hemisphere turns away from you, another rotates into view. Then the cycle repeats. There is no permanent dark hemisphere. There is only a constantly changing geometry between Mars, Earth, and the Sun. That distinction matters because it changes what far side really means. When the far side faces away from Earth, direct radio communication with a spacecraft there can become difficult or impossible if the spacecraft is operating behind Mars. The planet itself becomes a wall, a gigantic wall nearly 6,800 kilometers across. Radio signals cannot simply pass through it. For a mission operating near Mars, this creates one of the most dangerous moments imaginable. Silence. Your spacecraft may still be alive, its instruments may still be running, its computers may still be counting seconds. But Earth cannot hear it. Mission controllers can send commands before the blackout. They can calculate where the spacecraft should be, they can estimate what it should be doing, but they cannot continuously watch it. It is like sending a submarine beneath an ice sheet and then losing every sensor. You wait and wait and hope. Mars has already demonstrated how unforgiving this can be. The planet is littered with the remains of missions that failed to survive the journey. Some spacecraft never reached Mars. Some arrived but failed during orbital insertion. Some landed and stopped responding. Some operated for years before finally going silent. Others never even transmitted a single useful measurement. Space exploration is often remembered through its victories. But Mars remembers the failures. The planet has swallowed spacecraft from multiple nations, and Japan knows this better than most. Nozomi was supposed to become Japan's first spacecraft to enter orbit around Mars. The mission began with enormous ambition. Nozomi, meaning hope, was launched in July 1998. Its original plan involved a direct trajectory toward Mars, but problems with the spacecraft's propulsion system forced engineers to redesign the mission. A lunar flyby was used. Then additional Earth gravity assists. The spacecraft was effectively thrown around the inner solar system to conserve fuel. It was clever. It was necessary. And it was dangerous. The mission eventually encountered another devastating problem. A solar flare damaged the spacecraft's power and propulsion systems. The resulting loss of fuel meant that Nozomi could no longer achieve its intended Mars orbit. Engineers tried to salvage the mission. They succeeded in keeping the spacecraft alive far longer than its original trajectory should have allowed. But eventually the mathematics became merciless. Nozomi could not reach Mars in the way required. In December 2003, Japan abandoned the attempt. The spacecraft passed Mars without entering orbit. Think about what that means. Years of engineering, years of calculations, a spacecraft launched from Earth, a journey across interplanetary space, and at the end, Mars simply refused to let it stay. Nozomi became a reminder that reaching another planet is not one challenge. It is hundreds of challenges stacked together. Launch, navigation, power, thermal control, communications, propulsion, radiation, software, timing, and then finally orbital mechanics. Miss just one, the planet wins. That failure is important because Japan's return to Mars is not being designed as a simple sequel. It is a completely different philosophy. Instead of trying to force a spacecraft directly into Mars orbit and then remain there indefinitely, MMX will operate within the Martian system and use Phobos as its primary target. And Phobos is a bizarre target. From a distance, it looks like an asteroid. It is irregular, heavily cratered, dark, almost alien even by planetary standards. It measures only about 27 kilometers across at its longest dimension. That means you could cross it in a fraction of the time required to cross Mars itself. But its small size creates a massive problem: gravity. Phobos has so little gravity that landing there is almost the opposite of landing on Earth. On Earth, gravity grabs you. It pulls you toward the ground with tremendous force. On Phobos, the ground barely holds you. A careless movement could send you drifting away. Imagine jumping on Earth. You rise perhaps half a meter. On Phobos, the same instinct could become a launch. You would not feel anchored to the surface. You would feel like you were standing on a gigantic cosmic snowball. And that is precisely why a sample return mission becomes so difficult. The spacecraft must approach, match velocity, enter the correct orbit, descend toward a surface that is irregular and poorly understood, determine where the terrain is safe, touch down, collect material, ascend again, and then leave the Martian system. Every step requires extraordinary precision. There is no mechanic waiting nearby, no rescue vehicle, no emergency landing team. If the spacecraft becomes trapped on Phobos, it stays there. If a landing leg breaks, there is no replacement. If the sampling mechanism jams, the mission may lose its central objective. And if the spacecraft cannot escape the moon's gravitational environment, the sample never comes home. But the most fascinating part is what Japan hopes to find in those grains. Scientists are not simply looking for unusual rocks. They are looking for the origin story of the Martian moons. Because Phobos may be carrying evidence from the earliest chapters of Mars. If it formed from debris blasted away by a gigantic impact, its material could contain signatures connected to Mars itself. If it is a captured asteroid, the story changes completely. The sample could instead resemble primitive objects that formed elsewhere in the solar system. That would make Phobos something like a time capsule, a fragment from a distant neighborhood that somehow became trapped around Mars. And there is a third possibility that is even more interesting. The truth may be messy. Phobos may contain material from multiple sources: impact debris, asteroidal material, Martian fragments, dust transported from Mars. A geological mixture created over billions of years. The answer may not fit neatly into one category. That is what makes sample returns so powerful. You are not asking a spacecraft to give you a yes or no. You are bringing the evidence home. And once that evidence reaches Earth, scientists can compare it with meteorites already in our collections. They can compare it with Martian meteorites. They can compare it with samples from asteroids. They can compare isotopic fingerprints. And isotopes are where the story becomes almost forensic. Atoms of the same element can exist with different numbers of neutrons. Those variations can preserve information about where material formed. Think of isotopes as microscopic passports. A rock may look ordinary, gray, brown, dusty, unremarkable, but inside its atoms may be a chemical signature that tells you where it was born billions of years ago. That is what Japan is ultimately chasing. Not a photograph, not a spectacle, a fingerprint belonging to Mars, and perhaps to something that existed before Mars became Mars. Because When you strip away the red dust, the giant volcanoes, the canyons, the impact craters, and the endless empty plains, Mars becomes something else. A record, a planetary archive, and its far side is not a forbidden realm hiding alien cities. It is something more scientifically valuable, a region of a world whose story is still incomplete. The closer humanity gets, the more obvious the truth becomes. We have not finished exploring Mars. We have barely begun. And Japan's next attempt may not reveal a monster hiding beneath the surface. It may reveal something more disturbing, that the history of Mars has been sitting in plain sight for billions of years, and we have simply been looking at the wrong evidence. The moon that should not be there. Phobos should not look the way it does. It should not be hanging there above Mars like a broken piece of stone. It should not be racing around a planet at an altitude of only a few thousand kilometers. And it definitely should not be carrying one of the biggest mysteries in planetary science. But there it is, a dark, irregular object orbiting Mars so closely that from the Martian surface, it can cross the sky in only a few hours. Phobos rises, moves, and disappears again. Not because Mars rotates quickly, because Phobos is moving incredibly fast. It completes an orbit around Mars in roughly 7 hours and 39 minutes. Mars itself takes about 24 hours and 37 minutes to rotate once. That creates a bizarre situation. Phobos completes more than 3 orbits during a single Martian day. If you were standing on the surface of Mars at the right location, you could watch the moon rise in one direction, race across the sky, set, and then return again before the next sunrise. It would look almost unnatural, like someone had placed a moon on fast forward. And then there is its size. Phobos is tiny. Its longest dimension is only around 27 kilometers. Deimos, the other Martian moon, is even smaller. Neither resembles Earth's moon. There are no sweeping bright plains visible from Mars, no massive spherical body dominating the horizon. Instead, Phobos looks like a battered stone. Its surface is scarred, its shape is irregular, its gravity is weak, and one enormous crater dominates its appearance. Stickney. The impact crater is roughly 9 kilometers across. That means the crater occupies an astonishing fraction of the moon's entire body. Imagine punching a hole nearly 1/3 the length of Manhattan into an object only a few dozen kilometers wide. That is Stickney. And the crater may tell you something important about Phobos's past. But there is a problem. Nobody knows exactly what Phobos is. That uncertainty has survived for generations. 2 broad explanations dominate. The first is that Phobos is a captured asteroid. Mars may have encountered a wandering object in the early solar system. Gravity reached out, the asteroid lost enough energy, and suddenly it was trapped. A prisoner. The second explanation is far more violent. A massive impact may have struck Mars during its early history. The collision would have been catastrophic. Rock would have been vaporized, crust would have been shattered. Enormous quantities of material could have been blasted into orbit. Over time, that debris may have collided, merged, and formed the moons. If that happened, Phobos is not an asteroid. It is a relic of a planetary disaster, a piece of Mars's own violent childhood. And that possibility changes everything, because now Phobos becomes a crime scene. Mars is the body that was struck. Phobos is potentially part of the debris field, and Stickney may be another chapter in the evidence. The question is whether the material on Phobos resembles Mars. That sounds simple. It is not, because Phobos has been bombarded by material for billions of years. Every impact can throw Martian dust into space. Some of that dust can land on Phobos. That means the moon could contain traces of Mars even if Phobos itself did not originate from Mars. It is like finding a suitcase filled with sand at an airport. You know there is sand inside, but that does not tell you where the suitcase came from. The sand could have been packed deliberately. It could have been transferred accidentally, or someone could have dropped it there yesterday. The same problem exists on Phobos. Scientists need to separate native material from contamination, and that is exactly why a sample return mission is so valuable. MMX is designed to collect material from the surface of Phobos and bring it back to Earth. The spacecraft is planned to spend years operating in the Martian system. It will study Phobos from orbit. It will observe the moon's surface. It will investigate its composition, and then it will attempt something terrifyingly precise: landing, not on Mars, on Phobos, a tiny world with almost no gravity. The spacecraft will have to approach the surface at extremely low relative velocity. It cannot simply drop. There is not enough gravity to make a conventional landing straightforward. Instead, MMX must perform a carefully controlled descent and contact maneuver. Then the sampling system must collect material. The mission's goal is to return at least 10 grams of Phobos samples to Earth. 10 grams. That sounds laughably small. You could hold it between two fingers. But scientifically, 10 grams from another planetary system can be priceless. A teaspoon of material can contain billions of years of history. One grain may reveal mineral chemistry. Another may preserve radiation damage. Another may contain a tiny amount of organic material. Another may carry isotopic evidence pointing toward the origin of the moon. The quantity is small. The information may be enormous. This is why sample return missions are so difficult. You are not transporting a mountain. You are transporting a few grams of evidence across millions of kilometers, and you cannot afford to contaminate it. The spacecraft itself must be designed around planetary protection and sample preservation requirements. The container must survive launch, deep space, the Martian environment, the return journey, and atmospheric entry. Then, after all that, the sample must arrive in a condition suitable for laboratory analysis. Think about the absurdity of the mission. You spend years building a machine, launch it from Earth, send it hundreds of millions of kilometers through space, orbit another world, land on a tiny moon, touch its surface, collect dust, launch away, return through interplanetary space, and then throw the entire package back into Earth's atmosphere, all for a handful of grains. That is not excessive. That is the only way to do planetary science at the highest level, because laboratories on Earth have capabilities no spacecraft can carry. A spacecraft has strict limits: power, weight, computing, instrument size, temperature, radiation, but an Earth laboratory can contain machines weighing tons. You can build new instruments decades after the mission returns. You can develop new techniques that did not exist when the spacecraft launched. You can analyze the same sample again and again. This is the secret advantage of sample return. You do not just bring back rocks. You bring back future science. A sample collected in 2027 could still be studied in 2077, and perhaps in 2177. That is why Japan's previous sample return missions matter. Hayabusa returned material from asteroid Itokawa. Hayabusa 2 returned samples from Ryugu. Those missions demonstrated Japan's ability to perform precision operations around tiny bodies and return extraterrestrial material safely to Earth. MMX represents another step. This time, the destination is the Martian system, and the scientific stakes are much higher. Because Mars is one of the few places in the solar system where we have strong evidence that conditions were once potentially habitable. Water existed on its surface, organic molecules have been detected, complex chemistry exists. The planet contains enormous ancient river valleys, and yet today, Mars is cold, dry, and hostile. Something happened. The atmosphere changed, the climate changed, the planet lost much of its surface water. But when? Why? How? And did life ever have a chance to emerge before the environment collapsed? Phobos cannot answer every question, but it may preserve evidence about the conditions that shaped Mars. It may tell us about the planet's early evolution. And that brings us back to the far side, because when you look at Mars from Earth, you see a world separated from you by millions of kilometers. When you look at Mars through a spacecraft, you begin to see layers, ancient crust, volcanic provinces, impact basins, dust, ice, water-altered minerals, and enormous geological structures hidden on the opposite hemisphere. The far side is not physically mysterious. It is scientifically incomplete. And there is a difference. The mystery is not that Mars is hiding something from us. The mystery is that we have not yet collected enough evidence to reconstruct what happened. Every mission removes another piece of ignorance. Every crater photographed, every mineral identified, every atmospheric measurement, every gram returned. And perhaps that is the most important thing Japan's mission represents. Not a race to plant a flag, not a search for sensational monsters, but an attempt to recover evidence from a world that has been changing for billions of years. Mars is still keeping its secrets, but it is running out of places to hide them, and somewhere above its red surface, a tiny moon may be carrying the evidence. The evidence of an impact, the evidence of an asteroid, or the evidence of something we have not yet imagined. The spacecraft has not arrived, the sample has not been collected, the answer has not been written, but the search has already begun. And when Japan finally touches Phobos, the first thing it may discover is not what the moon is made of. It may discover that our entire story about how the Martian system formed was wrong. The giant scar on Mars. Mars has a wound so enormous that you could place an entire continent inside it. And for decades, scientists have argued over what caused it. You cannot see the full scale of the scar from the ground. You need to pull back farther and farther until Mars becomes a globe. Then the pattern begins to emerge. One hemisphere looks fundamentally different from the other. The northern lowlands are relatively flat and low. The southern highlands are heavily cratered and elevated. The boundary between them stretches for thousands of kilometers. This is the Martian dichotomy, and it may be one of the oldest clues to the planet's violent past. The difference is enormous. In some regions, the northern plains sit several kilometers lower than in the ancient southern terrain. The crust itself appears thinner in much of the north. Something created that division. But what? One possibility is that Mars experienced a gigantic impact early in its history, not a normal crater, not the kind of impact that leaves a circular scar several hundred kilometers across. Something much larger. An impact so powerful that it may have reshaped an entire hemisphere. Imagine a planet-sized billiard ball. Now imagine another enormous body striking it at cosmic velocity. There would be no explosion like a conventional bomb. It would be something far worse. Rock would melt, crust would fracture, material would be thrown across the planet. Shock waves would travel through the interior. The atmosphere would be disturbed, and the surface could be transformed on a scale that is almost impossible to visualize. This is one of the leading ideas behind the Borealis Basin hypothesis. The proposed basin occupies much of Mars's northern hemisphere. If it really was created by an ancient impact, it could be one of the largest impact structures in the solar system. But there is a problem. Mars has been attacked by time. Volcanism has covered portions of the surface. Wind has moved dust. Water altered minerals. New impacts created younger craters. The crust has been modified. The evidence is damaged. Imagine trying to determine who broke a window after the building has been abandoned for 4 billion years. The glass is gone. The frame has been replaced. The floor has been rebuilt. Dust covers everything. You are not investigating the original crime scene. You are investigating what survived. That is planetary science. And this is where the far side of Mars becomes important. The hemisphere facing away from Earth at a given moment contains enormous geological structures that help scientists reconstruct the planet's history. Some are obvious, others are buried. Some were photographed in astonishing detail by orbiters. Others require measurements of gravity, topography, mineral composition, and crustal thickness. You cannot understand Mars by looking at color alone. The red surface is misleading. That red comes largely from iron-bearing minerals altered and oxidized at the surface. Mars is not simply a red rock. Underneath the dust is a complicated geological machine. Ancient crust, volcanic rock, sedimentary deposits, impact melt, water-altered minerals, frozen reservoirs, and perhaps buried structures that preserve information from a time when Mars looked completely different. One of the greatest challenges is determining the age of these structures. Mars does not come with labels. There is no sign saying, formed 4.1 billion years ago. Scientists have to infer age from evidence. One of the most useful methods is crater counting. It sounds primitive. It is anything but. The basic principle is that older surfaces have generally accumulated more impact craters than younger surfaces. A surface covered in craters has probably been exposed for a very long time. A smooth surface with relatively few craters may be younger. It is like counting scars on a tree. More scars can indicate longer exposure. But the method has limitations. The rate of impacts has changed. Erosion can erase craters. Volcanism can bury them. Dust can soften their appearance, and secondary craters can create misleading patterns. So scientists combine crater counts with other evidence: mineralogy, stratigraphy, topography, gravity, and where possible, direct measurements from spacecraft. This is why every new mission matters. It adds another layer of evidence. And Japan's contribution to the Martian system may eventually help solve a particularly important question. Where did the Martian moons come from? Because if Phobos formed from material blasted out of Mars by a massive impact, then the moon could preserve fragments from a catastrophe that happened billions of years ago. It would be like finding pieces of the bullet after a crime. The impact itself is long gone. The crater may have been modified, but the debris remains. And if the chemical and isotopic signatures of Phobos match Martian material, the case for a Martian origin becomes much stronger. But if the samples resemble primitive asteroids instead, another story emerges. Phobos may be an outsider, a body that wandered through the young solar system before Mars captured it. That would tell scientists something completely different about the planet's gravitational history. And then there is an even stranger possibility. The moon could contain evidence of both, because Mars is constantly throwing material into space. Every impact launches dust and fragments. Some of that material can travel far enough to escape the immediate surface. Some can enter orbit. Some can eventually collide with Phobos. Over billions of years, the moon could have accumulated a thin layer of Martian debris. So even if Phobos began as an asteroid, it could now be carrying pieces of Mars. That makes the sample return mission almost forensic. Scientists will need to identify which grains belong to Phobos, which grains came from Mars, and which may have arrived from elsewhere. The laboratory work could become an archaeological excavation at microscopic scale, one grain at a time, one isotope at a time, one mineral at a time. And the implications reach beyond Mars, because Mars is not an isolated object. It formed from the same ancient disk of gas and dust that produced Earth, Venus, Mercury, asteroids, and the other planets. The solar system was once a violent construction site. Rock collided with rock. Planetesimals merged, bodies shattered. Some were thrown outward, others spiraled inward. The planets were assembled through impacts. Mars was one survivor of that chaos. If Phobos contains evidence from that era, it may provide a rare window into the construction process itself. And that matters because Earth has erased much of its own early history. Our planet is geologically active. Continents move. Crust is recycled. Volcanoes erupt. Oceans weather rocks. Plate tectonics destroys ancient surface material. The Earth you stand on is constantly being rebuilt. Mars is different. It is comparatively quiet. Its crust can preserve ancient scars for billions of years. Mars is therefore not just another planet. It is an archive, a damaged archive, a dusty archive, a partially burned archive, but an archive nonetheless, and the far side may contain some of its oldest pages. That is why the language surrounding Mars can sometimes sound exaggerated. People speak about hidden civilizations, ancient ruins, artificial structures, mysteries in the shadows, but the real mystery is already extraordinary enough. You are looking at a planet that once possessed conditions dramatically different from those of today. A planet with enormous volcanoes, a canyon system stretching thousands of kilometers, ancient river valleys, buried ice, a fractured crust, and perhaps the scars of collisions that altered an entire hemisphere. You do not need an alien city to make Mars terrifying. The geology is enough, and the more scientists learn, the more obvious one fact becomes. Mars did not simply become cold, it changed. Something happened to its atmosphere, its magnetic environment evolved, its surface water disappeared, its climate crossed a threshold, and eventually the planet became the frozen desert you see today. The question is whether that transformation happened gradually, or whether Mars crossed several catastrophic thresholds in its early history. The answer may be written in its oldest crust, and some of that crust may have been thrown into space long ago, then captured by gravity, then battered for billions of years, then left behind on a tiny moon, Phobos, a moon that may be nothing more than a cosmic accident. Or it may be the surviving evidence of one of the most violent events in Martian history. Japan is going there to find out. And when the sample eventually reaches Earth, scientists may hold something in their hands that has not touched our planet since the solar system was young. A piece of another world. A piece of Mars's forgotten childhood. And perhaps a piece of the catastrophe that changed the planet forever. Mission that has to touch a world with almost no gravity. Landing on Mars is terrifying. Landing on Phobos is something else. Because on Mars, gravity is strong enough to pull a spacecraft toward the surface with a predictable force. On Phobos, gravity is so weak that the rules of landing begin to feel almost backwards. You are not really falling toward the moon, you are negotiating with it. And Japan's MMX spacecraft will have to perform that negotiation perfectly. Phobos is only about 27 kilometers across. Its gravitational pull is tiny compared with Earth. Even Mars, which already has only about 38% of Earth's surface gravity, feels powerful next to it. Phobos is a different environment entirely. If you stood on its surface, you would weigh almost nothing compared with what you weigh on Earth. The ground would barely hold you. A careless jump could become a trajectory. A small error during descent could send a spacecraft drifting away instead of settling onto the surface. That makes the landing phase one of the most dangerous moments of the entire mission. But before MMX can touch Phobos, it has to survive something even more complicated. Mars. The spacecraft must travel from Earth into the Martian system. That sounds simple when compressed into a single sentence. It is not. Interplanetary navigation is a game of timing. Earth moves around the sun, Mars moves around the sun, the spacecraft moves around the sun. All three are constantly changing position. You cannot simply point a rocket at Mars and fire. By the time the spacecraft reaches the planet, Mars will have moved millions of kilometers. So engineers calculate a trajectory through a constantly moving solar system. Imagine throwing a ball at a moving train from another moving train while both trains are traveling around a giant circular track. Now remove the ability to see the target continuously. Then make the ball cost hundreds of millions of dollars. That is closer to the problem. The spacecraft is not traveling toward where Mars is. It is traveling toward where Mars will be. And the margin for error is brutal. A tiny navigation mistake at the beginning can become an enormous positional error months later. That is why missions use carefully planned trajectory corrections, small burns, small adjustments, tiny changes in velocity. Because in space, velocity is destiny. A change of just a few meters per second can alter where a spacecraft ends up thousands or millions of kilometers later. Then comes the Martian system. MMX will not simply approach Mars and dive directly toward Phobos. It must establish the correct relationship with the planet and its moon. Phobos is moving rapidly around Mars. The spacecraft has to match that motion. It is like trying to jump onto a train while both you and the train are already moving. Except the train is traveling through space. Except there is no track. Except the train is only a few kilometers wide. And except you cannot repair the spacecraft if you miss. This is why the mission has been designed with extensive scientific and engineering objectives before the sampling attempt. MMX is expected to study Phobos and Deimos, observe Mars, and investigate the environment surrounding the planet. The spacecraft carries multiple instruments designed to examine the moons from different perspectives. Cameras can map terrain. Spectrometers can analyze composition. Other instruments can investigate the physical environment and internal structure. One of the most intriguing instruments is a neutron and gamma ray spectrometer. Why? Because the surface of a world can hide information that ordinary cameras cannot see. Neutrons and gamma rays can reveal clues about elemental composition. They can tell scientists about the materials present in the upper layers of the surface. And that matters because Phobos may look like an ordinary dark rock while hiding an extraordinary chemical history. You could photograph a handful of Phobos soil and see almost nothing. Gray, brown, dusty. But the atoms inside it could tell an entirely different story. The spacecraft is therefore not just taking pictures, it is interrogating the moon, asking questions with light, questions with radiation, questions with gravity, questions with motion, and eventually questions with physical contact. The landing system is particularly important because MMX is intended to perform a surface sampling operation. The spacecraft will approach a selected region, it will descend, and it will briefly attack the surface. The mission design has to account for the strange mechanical behavior of Phobos. Loose regolith can behave differently in microgravity than soil behaves on Earth. A sampling mechanism designed for Earth-like environments cannot simply be copied and installed on another world. When you push into loose material under normal gravity, the ground pushes back. On Phobos, the response is far weaker. Material can move, particles can scatter, the spacecraft can recoil, and every gram matters. The sampling system therefore has to collect material without accidentally launching the sample into space. That sounds absurd, but on Phobos, even dust can become a projectile. This is one of the great paradoxes of small body exploration. The object is easier to escape from than to land on. You need enough control to make contact, but not so much force that you bounce away. You need to collect material, but not disturb the entire sampling site. And you need to preserve the sample because contamination could compromise the very scientific questions the mission was built to answer. Then comes the moment the mission has been designed around. The sample enters its container, a few grams, perhaps more. The material is sealed, and suddenly the spacecraft is carrying something that has been sitting on Phobos for an unknown length of time, maybe millions of years, maybe billions. Then the spacecraft has to leave. That is not guaranteed. The journey home is another enormous engineering challenge. The spacecraft must depart the Martian system with the correct velocity. Too little, it remains trapped. Too much, the trajectory may miss Earth. Again, the mathematics becomes unforgiving. And there is something deeply unsettling about this process. Once the spacecraft begins its return journey, the most important part of the mission is no longer on Phobos. It is inside a container, a tiny capsule carrying extraterrestrial material across interplanetary space. If something goes wrong with the main spacecraft, the sample could be lost. If the return trajectory is wrong, the sample could miss Earth. If the capsule fails during atmospheric entry, billions of years of geological history could disappear in seconds. So the mission is not simply a journey outward. It is a chain. Every link has to survive. Launch, cruise, Mars arrival, Phobos operations, sampling, departure, Earth return, atmospheric entry, recovery, laboratory containment. Only then can scientists finally begin the real investigation. And that is where Japan's previous experience becomes important. Hayabusa and Hayabusa 2 proved that Japan could perform delicate operations around tiny bodies where gravity is weak and navigation is extraordinarily difficult. Those missions were not flawless. They encountered failures. They required improvisation. They demanded engineers solve problems millions of kilometers from Earth. That experience becomes part of MMX. Every failure becomes knowledge. Every unexpected movement becomes data. Every recovered grain becomes evidence that the impossible can be made routine. But MMX carries a different emotional weight, because this time the destination is not simply an asteroid. It is the Martian system, a place that has fascinated humanity for centuries, a place once imagined as a world of canals, then a world of vegetation, then a dead planet, then an ancient wet planet, and now potentially a world that once offered conditions suitable for life. The closer you get to Mars, the less it resembles the fictional planet of old. It becomes more frightening, more complicated, more real. And the spacecraft will eventually approach a tiny moon hanging above that red world. Phobos, a moon that may be a captured asteroid, a moon that may be the remains of an ancient collision, a moon covered in material that may have come from Mars, and perhaps buried among that material, something that has survived since the earliest days of the planet. The spacecraft will not know what it is carrying. The engineers will not know. The scientists will not know. Nobody will know until the sample is opened. That is the beautiful cruelty of exploration. You cannot guarantee what you will discover. You can only guarantee that you are willing to look. And when MMX finally touches Phobos, Japan will not merely be landing on a tiny moon. It will be touching a fragment of the Martian mystery. For a few seconds, the spacecraft will make contact with a world that humanity has never physically touched before. Then it will rise again, leaving the surface behind, carrying dust, carrying rock, carrying history, and carrying one question all the way back to Earth. What happened to Mars? The dust that could rewrite Mars. The most important thing Japan may bring back from Mars will not be a photograph. It will be dust. A few grams of ancient material could force scientists to rewrite the story of an entire planet. That sounds impossible until you understand what a rock actually is. To you, a rock is a rock, something hard, something gray or brown, something you step over without thinking. But to a planetary scientist, a rock is a historical document. Its minerals record temperature. Its chemistry records the environment in which it formed. Its isotopes can preserve information about where its atoms came from. And tiny trapped materials can sometimes preserve conditions that existed billions of years ago. That is why the sample inside MMX will be so valuable. The spacecraft is not returning souvenirs, it is returning evidence. And the first question will be brutally simple. Is Phobos actually made from Mars? The answer could settle one of the oldest mysteries surrounding the Martian moons. If Phobos formed from debris ejected by a gigantic impact on Mars, scientists should expect its material to show some relationship to the planet, not necessarily an exact chemical match. The collision itself could have mixed different materials, but there should be clues. Mineral composition, elemental ratios, isotopic signatures, physical structure. Scientists can compare these characteristics against material already known to come from Mars, and that comparison could be decisive. Martian meteorites already exist on Earth. These rocks were blasted off Mars by enormous impacts and eventually traveled through space before falling onto our planet. They are extraordinarily rare, but they have already given scientists an unusual advantage. We possess physical pieces of Mars. The problem is that those meteorites are biased samples. You do not know exactly where on Mars each one originated. You do not know the precise geological context in which it formed, and you cannot simply walk back to the crater that launched it and inspect the surrounding layers. The rock arrived without its address. Phobos could provide something different. Its samples would come from a known location on a known body within the Martian system. Scientists could study not only the chemistry of the grains, but also their relationship to the environment in which they were found. That context matters. Imagine finding a single bone in a desert. Interesting. Now imagine finding the same bone inside an intact skeleton. Suddenly the information multiplies. Context turns an object into evidence. And MMX is designed to provide that context. Before sampling, the spacecraft will study Phobos in detail. Scientists can identify candidate regions. They can examine surface characteristics. They can investigate the moon's composition. They can look for variations across the terrain. Then the sampling location can be interpreted against the broader geological picture. The sample will not simply say, here is some dust. It may say, here is the kind of dust that exists in this specific environment at this specific location on this specific moon. That difference is enormous. But there is another possibility. What if the sample does not resemble Mars? What if Phobos looks chemically more like primitive asteroids? Then the entire story changes. Instead of being born from a Martian catastrophe, Phobos may be an ancient visitor, a body formed somewhere else and later captured by Mars. That would tell scientists that the early Martian system was capable of capturing small bodies. It would also give researchers a physical sample from a type of object that may resemble some of the primitive building blocks of the solar system. And now the mystery becomes even larger, because the solar system was not born as a collection of finished planets. It began as a rotating cloud of gas and dust. Gravity gathered material, particles collided, small bodies formed. Those bodies collided again. Some merged, some shattered. Some were thrown into different orbits. Eventually, planets emerged from the violence. The material inside Phobos may therefore preserve information from that ancient construction process. That is one reason primitive asteroids are so scientifically important. They can contain material that changed very little since the solar system formed. They are cosmic leftovers, the ingredients that never became a planet. If Phobos is one of those leftovers, its surface could contain a fragment of the solar system's original recipe. But Mars may have contaminated that recipe. The planet is constantly bombarded by impacts. Every major collision can eject material. Some of it can enter orbit, some can eventually fall onto Phobos. Over billions of years, the moon may have accumulated a layer of Martian debris. So even a captured asteroid could now carry pieces of its captor. That means scientists may need to separate two histories from the same sample, the history of Phobos and the history of Mars. The laboratory analysis could become an archaeological dig conducted at microscopic scale. One grain may belong to the moon, another may have originated on Mars. A third could have come from an impactor, and each may have a different story. The challenge will be identifying them. This is where isotopes become powerful. Take oxygen. Oxygen exists in several stable isotopic forms. The proportions of these isotopes vary among planetary materials. Those variations can act like fingerprints. Earth has its own isotopic characteristics. Mars has another pattern. Asteroids can have others. If Phobos material shares a distinctive isotopic signature with Mars, that becomes important evidence. If it does not, scientists have to reconsider the origin story. And this is why the sample could become one of the most important collections of extraterrestrial material ever returned to Earth. Because the question is not merely where Phobos came from, it is what that tells us about Mars. If Phobos formed after a giant impact, perhaps the Martian system experienced a collision powerful enough to throw enormous quantities of crust into orbit. That would give scientists clues about the scale of impacts during the early solar system. If Phobos was captured, scientists would gain evidence about the orbital environment around early Mars. If it is a mixture, the result could be even more complicated. And complicated answers are often the most valuable, because nature rarely respects the clean categories humans create. Mars may not have one simple origin story. Its moons may not have one simple origin story. The early solar system may have been a chaotic web of collisions, captures, fragmentation, and recombination, and Phobos may be one of the surviving witnesses. But there is another question hiding beneath all of this. Water. Mars once had it. We know this from geology. Ancient channels cut across the surface. Minerals formed in the presence of water. Sedimentary structures reveal environments that were once dramatically different from the frozen desert you see today. But how much water did Mars have? How long did it remain? Where did it go? And when did Mars become the planet we recognize today? Phobos may not directly answer all of those questions, but it could preserve clues about the materials that move through the Martian environment. Its surface may contain material ejected from Mars. That material could have interacted with water or atmospheric processes before being launched into space. If such grains can be identified, they may provide another indirect record of ancient Mars. And then there is organic chemistry. Organic molecules are not automatically evidence of life. That distinction is crucial. Organic chemistry can occur naturally. Meteorites contain organic compounds, asteroids contain them. Planetary environments can manufacture them without biology. But finding certain compounds in the right context can still reveal important information about the chemical ingredients available to ancient worlds. MMX therefore has the potential to investigate not only the origin of Phobos, but the movement of water and organic materials through the Martian system. That is a much bigger story. You begin with a tiny moon, you end with planetary evolution, you begin with dust, you end with questions about habitability, and you begin with a spacecraft built in Japan. You end with humanity holding another world between its fingers. That is the strange scale of planetary exploration. The object may be small, the question may be enormous. A few grams could tell you whether Phobos was born from Mars, whether an ancient impact reshaped the planet, whether a wandering asteroid was captured, whether material traveled between Mars and its moons, and perhaps how the early Martian environment evolved. But the most haunting possibility is that the sample tells us something about a Mars that no longer exists, a warmer Mars, a wetter Mars, a Mars with a thicker atmosphere, a Mars that may have remained habitable for long enough to allow chemistry to become something more complicated. You will never see that ancient Mars directly. It is gone. The rivers are dry, the lakes are gone, the atmosphere is thin, the surface is cold, but the evidence remains, buried in rocks, locked inside minerals, trapped within atoms, and perhaps resting quietly on the surface of Phobos, waiting for a machine from Earth to touch it, waiting for a sample container to close, waiting for a journey home. Because once those grains arrive on Earth, Mars will no longer be only a distant world in the night sky. Part of it will be here, in a laboratory, under microscopes, inside instruments, in the hands of scientists, and the planet that has remained silent for billions of years may finally begin to speak. The day Mars turned against itself. There may never have been a single moment when Mars died. No dramatic explosion, no cataclysmic impact that instantly transformed a living world into a frozen wasteland. The reality is more unsettling. Mars may have spent hundreds of millions of years slowly turning against itself. Planetary death is rarely sudden. It is gradual, a chain reaction, a series of small losses that eventually become irreversible. A world loses part of its atmosphere. The climate changes. Water becomes less stable, more atmosphere escapes. Temperatures fall, liquid water becomes increasingly rare. The planet crosses another threshold, then another, until eventually the world that once existed is gone. And Mars may be the greatest example of that process in the solar system. When scientists examine ancient Martian terrain, they find evidence that large quantities of water once interacted with the surface. Valley networks stretch across entire regions. Some resemble drainage systems created by rainfall. Others resemble river channels carved over long periods. Ancient lake basins have been identified. Sedimentary deposits indicate persistent interactions between water and rock. The evidence is not isolated, it appears across huge portions of the planet. And that creates an extraordinary possibility. Early Mars may not have been a brief accident. It may have remained habitable for significant periods of time, perhaps not continuously, perhaps not everywhere, but long enough for major geological systems to operate, long enough for water to shape the landscape, long enough for chemistry to become interesting. That possibility changes how you should think about Mars. Most people imagine a dead planet that was always dead, a red desert, cold, empty, hostile. But the ancient Mars suggested by geological evidence is different. Imagine standing beside a lake. Clouds move overhead, water flows through channels, minerals dissolve and redeposit. The atmosphere is thicker, the climate is warmer, the landscape is active. That world is difficult to reconcile with modern Mars, yet the evidence suggests it existed. Somewhere between those two realities lies one of the greatest transformations in planetary history. And this is where the far side of Mars becomes especially important. Not because it hides secret structures, not because it conceals alien technology, but because some of the oldest and most heavily cratered regions on the planet preserve records from the era when Mars was changing. The ancient southern highlands contain terrain dating back billions of years. These landscapes are geological museums. Their craters record impacts from the early solar system. Their minerals preserve evidence of environmental conditions. Their structure tells scientists how the crust evolved. And every new measurement helps reconstruct a vanished world. Think of Mars as a burned manuscript. Most of the pages survived, but many are damaged. Some paragraphs are missing. Some chapters are incomplete. The story is still there. You simply have to reconstruct it. And that reconstruction requires evidence from every possible source: orbiters, landers, rovers, meteorites, and now potentially samples from Phobos, because Phobos has spent billions of years circling above Mars while those transformations unfolded below. Imagine placing a camera above a city and leaving it there for 1 million years. The buildings would change, roads would appear and disappear, entire civilizations would rise and fall. The camera would witness everything,